This is now question 5 for June 2014 AQA AS Physics paper, Unit 1. Now, in question 5 we're given this circuit diagram and a student has altered the resistance and got this graph against power against resistance. And it's between 0.5 and 6.5 ohms. I mean, it isn't specific because simple answers, couldn't be bothered drawing it specifically, but a general kind of shape. I'll just let you, if you want to be pedantic, you can just copy and paste into the top right corner, alter the video, whatever. Anyway, so the first question is quite nice. It's more of a, it's actually, personally I think it's a question that looks harder, makes you think it can't be this easy, and well it is. It just says, explain what happens, describe how you would describe the power dissipated in Y, which is the variable resistor, in Y varies as resistance is increased from 0.5 to 6.5 ohms. So you just simply say the power increases to a maximum at 3 ohms of 3 watts. So it's sort of something like that. You would point out that point and say, well, then after that it begins to decrease at a non-linear rate. Okay, so that's pretty much just what you'd say. There's nothing more to that. Couldn't really add anything else. I mean, the key thing is you get the 2 marks from saying what actually happens to the power, and the other mark is for pointing out specific points, like when it becomes a maximum, what the resistance is and the power is at a maximum. Okay, so essentially I think it's quite a nice question. Nice 2 marks. 5b says the EMF of the battery is 6 volts. So the first thing I would write down before knowing anything else is that A equals 6 volts. Okay, we're also told in this question that the resistance of Y is set at 0.8 ohms. So even though it's variable, it's just set at 0.8 ohms. So you put big R, or Y, is equal to 0.8 ohms, 0.80 ohms. And this little r we don't know yet. Use the data to calculate the current through the battery. Okay, well, you can't use, so what we've got here is, it looks like we've got some kind of V, potential difference, when it's actually EMF, and R. So we're going to have to use some kind of power equation because we've got a power over here. Okay, so the only thing we can do is, we know that V equals IR, but we can't use that. So we've just got to think through our equations, but P equals IV, and you could say therefore P equals I, and then you put IR in the brackets, which gets you P equals I squared R. So could we use that? So they're the only 2 ones that you can consider. Now, we have to use this graph, so you go off where it's 0.8 ohms, because this is the resistance of Y. You go up and then you look at the power, and you should read off a power of about 1.95 watts. So therefore you say the power is 1.95 watts. We don't know the current, but we know the resistance, so we can use this formula. We just use the last bit, it's just explaining how you get to it. So therefore you put 1.95 watts is equal to I squared times 0.8 ohms. So therefore you rearrange this to get I squared as a subject, so therefore I is equal to the square root of 1.95 over 0.8. So therefore that should get you a current I, see it's in terms of amps, of 1.5. Now it says here 4, so this is negotiable, so it could be 535 or whatever, but they've rounded it to 1.54 amps. Okay, so that's the current going through the battery. So that's your 3 marks there. The next one, it says calculate the voltage across Y. Well, we just use this equation V equals IR. Now the voltage, the potential difference across Y, is the reason it's not asked us across the whole circuit because we don't know the internal resistance of the battery. So therefore the only thing we can do the potential difference across is the Y. If it had said the terminals, then we would have had to include the internal resistance as well in this equation, but that would probably get asked that, weirdly enough, in the next question. So anyway, so this is 5b part 2. So you just do potential difference across Y. So V equals IR. We know what I is, which is we just worked it out. So you could just copy this in from your calculator. So it's 1.54 amps times the resistance, which is 0.8 ohms. Okay, and if you would sub that in your calculator, you would get a voltage of 1.2 volts, or potential difference of 1.2 volts across Y. So remember, that's not the potential difference across the terminals, it's just the potential difference across Y. Right? Next one, so 5B part 3, asks us to calculate the potential the internal resistance of the battery. Now, something we haven't used this EMF, this E of 6 volts yet, so we're probably going to have to use this at some stage. And seeing as this is the last calculation question 5, we're going to have to use it, because it wouldn't tell you something that isn't needed. Okay? So anyway, so we've got to use some kind of well, we look at the equations on your formula sheet. The ones that involve E are E equals big E over Q, so it's electrical energy per unit charge, or E equals I brackets R plus little r, so it's E equals IR plus I little r. So you could do E equals V plus IR if you wanted to, or use that equation. They both come out with the same thing. Okay, so I'm just going to use this one because it breaks it up quite nicely. So therefore you just do, so just something what you know the EMF is 6 volts, you know the current is 1.54 amps. I mean, it did tell you what V equals IR was here, and we've worked out V, so you might want to use V equals I big R, and you could change that to V, so V equals V plus I little r, but that's completely up to you. So it's 1.54 times the Y resistance, which is 0.8 ohms, plus little r. You rearrange that, so you do 6 over 1.54, so 6 volts over 1.54 amps is equal to 0.8 ohms plus little r. So you rearrange that to get r as being 3.846 take 0.8, which gets you r to be 3.1 volts. Okay, so that's the internal resistance of 3.1 volts, which seems a lot, but it's not in comparison to the other part. So this is potential difference. Sorry, 3.1 ohms. Sorry, so it's not that much. It's, in reality, because this Y is extremely small. Anyway, so you'd have to worry about that. That is the correct answer. It's actually 3.09, but they round it up to 3.1 in the answers, as I have done in mine as well. Okay. So the next question, again, is a wordy one. Well, actually, you know what? I'll do this in the other way, just to so you can take it again. You've been revising that a little bit longer. So what we said was E equals IR plus little r. So you could just expand that out. So E equals IR plus I little r. And as we know, V equals IR. So you sub V into the equation. So E equals V plus I little r. And as we've just worked out what the potential difference is, it's something what we know. So 6 volts equal to 1.2 volts plus the current, which is obviously the same all around, 1.45 times little r, and you would rearrange that to get r as 3.1 ohms. Okay, so you would get the same answer doing it this way. I think that was a little bit quicker. They're both about the same, really. Anyway, so that's essentially what you do. Alright, so hopefully that made some kind of sense. Alright, right, so that's what you do for 5B. Now 5C part 1, because it's only one 5C. The student repeats the experiment with a battery of the same EMF but negligible internal resistance. State how and explain how you would expect the power dissipated in Y to vary as the resistance of Y is increased from 0.5 ohms to 6.5 ohms. And well, the power would just decrease as R increased, and there would be, as there is no internal resistance. Okay, so The first bit, you need to say the power will decrease as R increased because we've got no internal resistance, and therefore if we have no internal resistance, we've got to think about this formula over here. So E equals V plus I little r. So if little r is 0, this would end up being E equals V. So what that's saying is the EMF is equal to the potential difference if there is no internal resistance. And it's key to saying that, and I would actually put that equation in your explanation and show it. You need that second mark, that second point, to say therefore power is proportional to 1 over R with a constant of the potential difference squared. So basically power is V squared over R because we've not got any internal resistance. Okay? So you could rearrange the power equation to get that. Right, so that's essentially what would happen. Sorry. Alright, so as I say, that 5C I think is a little bit tricky, but I don't think I could explain that any better than it says on the mark scheme, because I think the mark scheme is quite clear on 5C. So if you still don't get what I'm waffling on about for 5C, please do check out the mark scheme, because I think that says most of what I've said. Alright, so I personally would have included that, as I said, I would have included this equation in your answer for 5C, but that's totally up to you. I think it would just help. You need to mention it anyway, so you might as well just be lazy and show it. Alright, you didn't need to draw that, and I was just showing you the graph. Okay, so hopefully that's been helpful, and we'll see you in question number 6.